Morning, everyone. How's everybody doing? Questions while we wait? Open window like the midterm. How are we doing? Good morning, everyone. How long will the final be compared to the midterm? I think we'll have a shorter final. Yeah. Well, I mean, I think it's going to be shorter. People might disagree, but I think it's going to be shorter. How's everybody doing with antiderivatives? Yeah, 18 questions was certainly enough. I think the final will be shorter. How are we doing with the antiderivative here? Questions? Questions on anything else while we wait? Anybody? No? We're good? Why don't I give you a few antiderivatives? Well, I mean, here's the thing with related rates. I would certainly prefer that you give me a related rates question if you want to do one. I have posted a past final exam. Let me just quickly see if there is a related rates question there. I suppose there is. There's usually one. There is not a related rates question. Oh, no, there is. There is. Very good. So we can always do that one when we get there. Arya is asking for a point like the web work question. Find the point on the line, which is closest to another point. If you have done 133, you know how to do that using 133 methods, right? Let's look at this question first. Related rates and optimization questions are quite similar. That's right, Sheridan. I mean, there were problems that you have to translate into mathematics, certainly. Secondly, I mean, in the related rates question, as the question suggests, you have to find a relationship. So that's the important thing. In optimization, sometimes you do, sometimes you don't. But yeah. So, you know, I mean, they are similar. Let's look at this. Let's do a few integrals while we're waiting for everybody else to come in. You know what to do, right? You know the antiderivative of powers of x. First of all, you have this constant here that you can disregard, just leave outside. The antiderivative of x to the 0.8 is 1 over 0.8 plus 1, x to the 0.8 plus 1. And similarly here, 1 over minus 2.5 plus 1, x to the minus 2.5 plus 1. Throw in your arbitrary constant, maybe clean that up. 3 over 1.8, x to the 1.8. Minus, if you will, 1 over 1.5, x to the minus 1.5. You can leave it as is, that's fine. There you have it. Morning, everyone. Come on in. How's everybody doing? Just doing a few antiderivatives while people are trickling in. I haven't written anything yet. I think it's going to be different. I think the final is going to be different from the midterm. We'll see. We'll make an announcement. In the meantime, you know, just make sure you're comfortable with the material. Lots and lots of exercises from the book. That's what you need to do. If you're comfortable with the material, you'll do very well. Consider this. You know what to do. Can we do this in our heads, in fact? Antiderivative. Sean likes some numerical constraints. I'm not sure what you mean by that. Oh, numerical constants, sorry. On the final, well, we'll see. I mean, you should expect some, right? I mean, we had a lot on the midterm. You should expect some on the final. I don't know that there are going to be a ton, though. Oh, you mean instead of the A's and B's? Well, if you can do with numbers, you can do with A and B. 4th root of 5 is a constant. That's right. That's why I have 4th root of 5x. Right? It's like if this was 2, the antiderivative would have been 2x. I don't know how many questions. I think less than the midterm. I think so. Midterm might have been a bit too long. I'm looking to make it kind of short. But then sometimes I get carried away. Yeah, well, you say short and sweet, but then when I give an exam that's too short, people complain that the questions were worth too much. So, I mean, it's a double-edged sword, right? I can do a midterm, I can do a final exam with 6 questions, but if 6 questions are worth 40%, and for some of you who transfer the weight of the midterm onto the final, if we have 6 questions worth 70%, then you see, yeah, exactly. Exactly that. Sheridan, I'm not looking for the derivative here. You know that this is notation for the antiderivative. So we're going backwards here. The derivative of this is that. Is that clear to everyone? Consider this. You know what to do. Yeah, I mean, Julia and Matt, I will keep that in mind. Maybe if I do give some variables there, I'll put constraints so that you don't have to do a whole bunch of cases. Absolutely. Pia, is it fair to say that antiderivatives have a bit of trial and error? Not so much. No, because remember here, we are using a formula, right? We saw the antiderivative of a power of x from working backwards with the derivative, right? The antiderivative is going to be 1 over n plus 1, x to the n plus 1. This is as long as n is not negative 1, and in the case that n is negative 1, the antiderivative of 1 over x is ln of absolute value of x. And that's all we're looking at so far. Coupled with the fact that the antiderivative is linear, because the derivative is linear, right? So the antiderivative of a sum is the sum of the antiderivative, so you can take the antiderivative of each part, and you can pull constants out. This is a constant, so you can pull it out, and we're looking for the antiderivative of 1, or x to the 0, which is x to the 1. So there's no trial and error here. We have these these two formulas for sure. The fact that the antiderivative is linear, and the fact that you know the derivative very well. So you can spot the antiderivatives of some functions just by looking. Here, the point is that you don't want to be making up your own rules for antiderivatives, right? You look at this and you're thinking to yourself, I have a quotient, so perhaps some sort of quotient rule is to be applied. It is not. Don't be making up your own rules. It's not going to go well. Instead, can we rewrite this in a way that is manageable? Can we rewrite this as powers of x? And we can, by splitting it up into 3 pieces. Right? You can rewrite that as 5x squared over x squared minus 6x over x squared and 4 over x squared. Simplify that. 5 minus 6 over x plus 4 over x squared. And now all you have are powers of x. And you can use these formulas here to help you find the antiderivative. What function has as its derivative 5? 5x. Pull out the negative 6, and you're looking for a function whose antiderivative is 1 over x. Well, you have it right here. Pull out the 4, and you're looking for a function whose derivative is 1 over x squared. You're looking for the antiderivative of x to the negative 2, which is negative 1, x to the negative 1. So negative 1, x to the negative 1. Throw in your arbitrary constant, and there it is. Is everybody with us? How are we doing? Questions on these antiderivatives? All good, right? Let's do just a few more. Why is the 4 negative? Right, we're looking at the antiderivative of 1 over x squared with the 4 outside, right? Because you can forget about constants. And this is really x to the negative 2. So the antiderivative of x to the negative 2 is 1 over negative 2 plus 1, x to the negative 2 plus 1. Negative 2 plus 1 is negative 1. So there it is. This is negative 1. That's why it's minus. Here it is. Same thing, right? This is 10x to the negative 6. Why don't we rewrite it that way? 10x to the negative 6. So what is the antiderivative? Forget the 10. What is the antiderivative of x to the negative 6? Formula works out nicely here. 1 over negative 6 plus 1. X to the negative 6 plus 1. Minus 2 is a constant. What is the antiderivative of e to the x? What function has derivative e to the x? You know what it is. It's e to the x. The derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. Finally, what function has derivative 3? X. Add in your arbitrary constant and you're done. Minus 6 plus 1 is minus 5. So 10 over minus 5 is minus 2. Had we done this one? Seems oddly familiar. Very well. So my question to you is, do we know of a function whose derivative is secant squared? Exactly that. Tangent x. Leave the constant pi outside. Do we know of a function whose derivative is cosine? Sine, and that's it. Let me ask you this. What about the antiderivative of cos? Oh, we just did the antiderivative of cos. That's not what I want. What about the antiderivative of sine? Right? Because you know the derivative of cosine is negative sine. So if you throw in a negative in front of that, you're good to go. The derivative of cos is going to be negative sine. Coupled with this negative that's outside, turns it into a positive, and you know it's right. Now, don't let the v fool you, whether it's x or it's v, right? And the same as with the derivative, whether you're differentiating with respect to x or you're differentiating with respect to v, It's just a dummy variable. Do we know a function whose derivative is 1 over 1 plus v squared? Anybody? If this had been an x, thank you, Olivia, the arctangent function, arctan v, has derivative 1 over 1 plus v squared. Absolutely. What about this one here? Do we recall a function which has this as its derivative? Matt suggests arcsecant, not quite. Instead, arcsine. Arcsine it is. Throw in your arbitrary constant. There you have it. How are we doing here? Questions? Anybody? All right, that's all I had for antiderivatives. What is the derivative of arcos? The derivative of arcos, so I see what you're suggesting here, right? The derivative of arcos x, you know to be negative 1 over square root of 1 minus x squared. So you're thinking to yourself, couldn't this also be arctan plus arccos? Absolutely. 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 So you could, if you viewed it as plus arccos instead of minus arcsine, very nice. Does the dx in the integral expression just mean with respect to x? Let's view it as that for this course, absolutely. Absolutely, right. It just tells you what variable you're working with. Yes. Questions? Can you integrate inverse trig functions? Yes, you can. Yes, you can. I want to say it's this. Let's check. Let's check by differentiating this business. I'm actually going to change it to a plus now. I think I've noticed my mistake. Right, let's check by differentiating this. Here you've got a product. So product rule applies. We'll differentiate the first one, leaving the second one fixed. And then we'll leave the first one fixed and differentiate the second one. The derivative of inverse sine is 1 over square root of 1 minus x squared. So that's the derivative. These two together are the derivative of this. Now we'll differentiate this. You've got a square root. So the derivative is 1 over 2 square root times the derivative of the inside. The 2's cancel out nicely. And we have arc sine x plus x over square root minus x over the square root. These cancel out nicely, leaving you with arc sine x. Very nice. Not something I expect you to know by heart, but rather a technique that we will investigate next semester. Questions? The derivative of cosine squared of x minus cosine of x squared like this. We can do that. We can do that. Well, I mean, what's the difference between capital X and small x? I don't think there's a difference, right? I mean, so if it was like arctan x, for arctan it would be different. For arctan it would be different. I'm going to let you verify that the antiderivative of arctan is x arctan x minus 1/2 ln of 1 plus x squared. Yeah, Talia, there's no difference. I mean, you're differentiating with respect to big X, and you've got big X's here. Big X is the variable. So there's no difference. It's just a dummy variable, right? In the same way that your integral is with respect to V, or if this was d by dv and you had V's here, it's all the same. No, it has nothing to do with the antiderivative. Absolutely. For completeness, let's just finish it up though. We've got something squared here, so the derivative is 2 cos times the derivative of the inside. Inside is cos, derivative of cos is negative sine. Here you've got cosine of something, whose derivative is negative sine of that something, times the derivative of the inside. So minus 2 sine cos plus 2x sine of x squared. Somebody wanted me to do some mean value theorem question. In fact, or mean value, and I think intermediate value theorem, I think there's one on the by the way, Michael, did you work out did you take the derivative of the proposed antiderivative here to make sure that it was what we were dealing with. So there were two questions. First of all, somebody wanted us to do a related rates or something. So let's look at number 4 in the long answer questions. Coffee is draining from a conical filter of depth 10 centimeters and diameter 10 centimeters at the top. So you've got a cone of height 10 centimeters and what was it? Diameter 10 centimeters here as well. So this is dripping into a cylindrical coffee pot. Maybe some handle here. Into a cylindrical coffee pot of diameter 12 centimeters. At a rate of 100 centimeters cubed per minute. So this is draining at a rate of 100 centimeters cubed per minute. How fast in centimeters per minute is the level of the coffee in the pot rising when the coffee in the filter is 3 centimeters deep? So how fast is the level in the pot rising when the coffee in the filter is 3 centimeters deep? And I mean, you all drink coffee, so this is an obvious question that has arisen. I am getting this question from the final exam I posted on my courses. I've posted a link to an old final exam in the announcements. Because, we have run out of material. So from now on, we're just going to answer questions and, time permitting, do that final exam. So since people wanted a related rates question, let's start with that. Somebody also wanted a mean value or intermediate value theorem question. Well, I think there's one. I don't have answers, but we'll probably do it. We'll probably do all of it in class. If the Sealan is asking if the rate is constant, then the level in the pot should always be rising at the same rate. Correct? In fact, that is correct. So the fact that you're 3 centimeters deep here will not play a role. Absolutely. Well, I wouldn't mind doing this year's final. The problem is it hasn't been written yet. So who knows what's going to come up on that. If only I had written it already. Yeah, so sealant is absolutely correct. The cone will not play a significant role in this question. But let's not worry about that right now. And because you know, you might not realize this immediately, and that's fine. That is fine. What do we want? So let's translate everything into mathematics, figure out what we want, and see what happens. How fast is the level in the pot rising? Well, so we want, right? I mean, you're going to have some coffee here of height h. Let's introduce some variables. We want, so let h be the height of the coffee in the pot. We want dH dt. That's what we want. Does the coffee drain slower over time? Apparently not, right? Apparently, the question suggests it's coming out at 100 centimeters cubed per minute. We are assuming nothing gets clogged, right? So, you know, like I said, let's not assume anything. Let's introduce some variables. Height, h is the height of the coffee in the pot. We want dH dt. That's what we want. What are we given? We are given that coffee is coming into the pot at this rate. What does that mean? This is you're getting 100 centimeters cubed of coffee per minute into the pot. This is the rate of change of the volume. dV dt is given to be 100. Exactly that. dV dt is given to be 100. We want dH dt. Is there a relationship between H and V? Well, V is the volume of coffee. What is the volume of coffee? How much coffee do you have if you have H being the height of coffee? You have a cylinder. So area of volume of a cylinder is pi r squared h, where r is given to be 12. Right? Thank you, Michael. Sorry. 12 is the diameter. Radius is 6. So not 144, but 36. Treat r as a constant because it is a constant, right? It is given to be 6. The diameter was 12, the radius is 6. Thank you, Kamal and Sean there. So you see, you have this nice relationship between volume and height. This question was very, very easy. The cone was just there to throw you off. Doesn't matter where it's dripping from. It's the rate at which volume is entering the pot that's important. So you see, so V is 36 pi h, and if you differentiate both sides with respect to t, 36 pi dH dt. This is what you want, and you have this given as 100. So dH dt is 100 over 36 pi. And as Seelan had suggested, first of all, does not depend on the cone at all. And the rate of change of the height is constant. It doesn't depend on this 3 centimeter deep either. A lot of stuff was given here, completely useless. Is the volume decreasing though? Right? This V is the volume of coffee in the pot. The volume is increasing. Exactly. It would be decreasing in the cone, but it's increasing in the pot. No, this volume here is the volume, right? Because H is the level of coffee in the pot, not in the cone. There it is. This is centimeters per minute. All right, let's try. Let's look at number 5. Prove that the function x cubed plus 9x squared plus 33x assumes the value -8 at least once. And there's a follow-up question. Using mean value theorem or Rolle's, no other method will be accepted. Prove carefully that this function takes on the value at most. So you see, conclusion, that it takes on the value exactly once. All right, you know what to do, right? Let's introduce that function p of x, p as in polynomial, right? You know this to be a polynomial. P of x is a polynomial, so you know it's well behaved. It's continuous everywhere, differentiable everywhere. Right? I mean, it's important to state that. But there it is. So continuous and differentiable everywhere. P of 0, when you plug in 0, this is easily seen to be 0. P of -1, what is that? That's -1. Plus 9 is 8. Minus 33, that is minus 25, is that correct? Minus 25? Anybody? Thank you. So by the intermediate value theorem, since P of x is continuous on the closed and bounded interval -1 to 0, and -8 is between -25 and 0, then there exists a value r in the interval -1 to 0 such that P of r is -8. Right, intermediate value theorem gives us that your function has to be -8 somewhere, right? I mean, from the graph, you know what's happening, right? At 0, you're at 0. At -1, you are at -25. So you're right here, and you know, whatever happens, to get from -25 to 0, since your function is continuous, it has to be -8 somewhere. This is your value of r. Since you can graph it without lifting the pencil from the paper, it has to be -8 somewhere. All right, well, so that's the first part. Right. Your function has to cross -8 at least once. Now we want to show that it doesn't cross it more than once. So suppose it crosses it twice. Suppose A and B are such that P of A is -8, and so is P of B. And let's say that A is less than B. Right? First of all, you want them to be different. So it's either this or the opposite, but if it was the opposite, you just rewrite them. So all I'm saying is I'm calling A the smaller of the 2 points. Well, I mean, you recognize that you're in a Rolle's theorem situation, right? P of A is equal to P of B, or, it doesn't have to be Rolle's theorem. Let's just do the mean value theorem. You know that Rolle's theorem is a special case of the mean value theorem. So apply the mean value theorem to your function on the closed and bounded interval AB. P is continuous on the closed and bounded interval AB and differentiable on the open interval, since P of X is a polynomial. Thus, by the mean value theorem, what are the implications here? There exists a C in the open interval AB such that what? Such that P of B minus P of A over B minus A is equal to the derivative at C. Right, you remember the mean value theorem, which was the implication here on a graph. If you look at the line joining the two endpoints, there exists a point where the slope of the tangent line is the same. Well, that doesn't look the same at all. Better. Where the slope of the tangent line is the same as the slope of the line joining the two endpoints, right? So this is the slope of the line joining the two endpoints. This is the slope of the tangent line. But what is this? P of B is -8, and so is P of A. So -8 minus -8 over B minus A. In other words, this is 0. Your derivative should be 0 somewhere. This is what the mean value theorem implies here. But what is the derivative? What is the derivative? The derivative is 3x squared plus 18x plus 33. So the derivative at C is 3c squared plus 18c plus 33. This derivative should be 0 somewhere. All right. Well, I mean, we can factor. Take out a 3. C squared plus 6c plus 33. Sorry, plus 11. But factored out of 3, make it simpler. So this product should be 0. And you know that if a product is 0, one of the factors has to be 0. So either 3 is 0, which it isn't. So you need c squared plus 6c plus 11 to be 0. So when is this 0? You can try factoring. It's not working out so well. What are you going to do? Just because you can't factor doesn't mean it doesn't factor. But as Michael suggests, we have a quadratic here equal to 0. So we can use a quadratic formula to find the roots. C is negative b plus or minus square root of b squared minus 4ac. That's a terrible choice here because I'm already using c here, but you know what we're talking about here. All over 2a. And you realize this is 36 minus 44. So this is negative 8. And you cannot take the square root of a negative number. So this is not a real number, no real roots, which is a contradiction because the mean value theorem guaranteed the existence of a point C where the derivative was 0. Not only of a point C, but a point C in the interval minus 1, 0. And this tells us that no such point exists. So an assumption we made must have been false, and the only assumption we made was that we had 2 points where the function was negative 8. You can just use the discriminant, but I mean you have to make this conclusion. Conclusion, so there is at most 1 point where the function is negative 8. User is asking, how can we assume that P of A is equal to P of B is equal to negative 8? Well, the question asks to show that there's at most 1 point. So what's the opposite of at most 1? The opposite is more than 1. And if you've got more than 1, then you have at least 2. So we assume that you have 2 points, and we get a contradiction. So that assumption must have been wrong. Sean is asking if we can do this another way. The question specifically said, using mean value theorem or Rolle's theorem, no other method is allowed. So we are doing review from now on, in the sense that come armed with questions, we can answer those. If there are no questions, we're going to do questions from the fall 2004 exam that I've posted online. So user is asking if we were asked to show there's at most 2 points you would start with the assumption that you had 3. Exactly that. And it is a valid question, and these things do come up. So if you want to prove that there's at most 2, you start with 3 and you show that you end up with a contradiction. Absolutely. How are we doing here? Questions? This looks like a good place to end. Thank you all for coming. On Wednesday, we'll continue with questions from the fall 2004 exam. Unless there are things you want me to go over specifically, we can do that to start. You guys have a good one. I will see you on Wednesday.